All right, in lesson 1.6, we looked at how the limits relate to infinite sequences. Now we're going to tie that into series. Now, remember, the difference between a sequence and a series is a sequence lists out the term values, T1, T2, T3, so on and so forth. A series takes the sum of all of those. So we replace the commas with a plus or minus. We can also denote this using sigma notation, where with this sigma notation, what it's really saying is that we're taking the sum from n equals 1 all the way to n equals infinity. And we can see that here and here. So for the first investigation, it says, does it make sense to determine the sum of a series such as 1 plus 2 plus 3 plus 4 plus 5 plus whatever going on to infinity? And so we can take a look at the partial sums. Now, we should know that the partial sums, the sum of the first term is literally just what the first term is. So it's just going to be 1. The sum of the first two terms is if I took term 1, combine it with term 2, or 1 plus 2, which is going to equal 3. The sum of the first three terms is just going to be 1 plus 2 plus 3, which is 6. First 4 is going to be 1 plus 2 plus 3 plus 4, which is going to be 10. 1 plus 2 plus 3 plus 4 plus 5 is going to give me 15. And then if it said, what is the sum of the first 16 terms, we could also calculate that, taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, add them all together, and I get 136. So what's happening? As n is increasing, the numbers are getting larger and larger and larger for the sums, which means that if I kept going to infinity, there is no specific sum that this is going to tend towards. What about the second case, where if I had 1/2, 1/4, 1/8, 1/16, all the way to 1/2 to the power of infinity? Well, the first one is just going to be what the first term is, 1/2. The second one is going to be 1/2 plus 1/4, which is 3/4 or 0.75. When I add up the first three terms, that's going to give me 7/8 or 0.875. First four terms is going to give me 15/16 or 0.934. And then this is going to give me 31/32 or 0.96875. And we can see that the sum is continuously getting closer and closer and closer to the value of 1, which means that we could say that the limit as n approaches infinity of this series, remember, because it's a series, we're saying Sn instead of Tn for a term value. For the series, when I'm adding them together, that's approaching 1. So how do we know whether or not it has a sum? We can define the partial sums as term 1 and term 2, term 1, term 2, term 3, so on and so forth, all the way up to whatever the last sum is. If the infinite sequence for S1, S2, all the way to S infinity of the partial sums is just adding the series together, and we say if it has a limit, then the sum of the series is L, and we can say that if we add up all the terms, it's going to be L, or if I take the sum starting at n1 all the way up to n infinity of t of n is just going to be my L value. And this would be the same as the sum to infinity. If the series has a sum or a limit, we call it convergent. If it does not have a sum or a limit, we call it divergent. These are, once again, two terms you learned in the unit in Math 20-1. Convergent is coming close together. Divergent is going to get further apart. And we also, as we've already seen in the last lesson, include oscillating in terms of divergent or not having a limit. Which means that in the first case, if I took 1 plus 1 plus 1 plus 1 plus 1 forever, then the limit of this does not exist because this is divergent. The sum is just going to continually get further and further apart and not come towards a set number. If I combine 1 and -1 and 1 and -1 going on forever, it's just going to keep jumping between a sum of 1 and a sum of 0, which means that, once again, this does not exist because it is oscillating, which in this case is going to be a divergency. When we're finding the sum of a geometric series, so if I have a sequence 2, 4, 8, 16, where I'm just multiplying each term by 2 to get to the next term, then I'm going to say that I have A, which is my first term. I'm multiplying it by R, my common ratio. And then I'm just going to keep multiplying it by the common ratio over and over and over again to get from one term to the next. So A is our first term. And R is the common ratio. Now, for a geometric sequence, to solve what any term value was, we always just use the formula. The sequence or the term value is equal to the first term times the common ratio to the power of the term placement minus 1. To find the sum of terms of a geometric series, we use the formula. The series sum is equal to the first term times 1 minus r to the power of n over 1 minus r. This told us any series sum.